For centuries, humanity has asked a single haunting question. What is the universe made of, and why does it exist in the form we observe? As a physicist, I have spent my life chasing a deeper version of that question. Not merely what the universe is made of, but whether there exists a single, elegant equation capable of describing everything, from the birth of the cosmos to the motion of electrons inside an atom. This ultimate equation is what I call the God equation. When I use the phrase God equation, I am not speaking of theology or religion. I am speaking of mathematics. I am speaking of the final law of physics, a compact mathematical framework that would unify all forces of nature and explain the structure of reality itself. Albert Einstein once said that he wanted to know whether God had any choice in creating the universe. By this, he meant whether the universe is inevitable, governed by necessity, or whether it is a random accident. The God equation would answer that question. Modern physics is built on two pillars, both astonishingly successful, yet fundamentally incompatible. On the one hand, we have quantum mechanics, the theory that governs the microscopic world of atoms, particles, and fields. Quantum theory explains the behavior of electrons, photons, quarks, and all the building blocks of matter with extraordinary precision. It underlies modern technology, from transistors to lasers to computers. On the other hand, we have Einstein's theory of general relativity, which describes gravity and the large-scale structure of the universe. It explains black holes, the expansion of the cosmos, gravitational waves, and the curvature of space-time itself. Individually, these theories work beautifully. Together, they fail spectacularly. When we attempt to combine quantum mechanics with gravity, the equations explode into infinities. The mathematics breaks down. The universe at its most fundamental level refuses to be described by our current tools. This conflict represents the greatest unfinished problem in physics, and resolving it is the central goal of the search for the God equation. Today, we recognize four fundamental forces that govern the universe. Gravity shapes the motion of planets, stars, and galaxies. Electromagnetism governs light, chemistry, and atomic structure. The strong nuclear force binds protons and neutrons inside atomic nuclei. The weak nuclear force governs radioactive decay and plays a crucial role in stellar fusion. The dream of physicists is to show that these four forces are not truly separate, but rather different aspects of a single, unified interaction. Quantum mechanics has already succeeded in unifying three of these forces. Electromagnetism, the weak force, and the strong force are all described within the framework of quantum field theory, culminating in what we call the Standard Model. Yet gravity stubbornly resists quantization. When we attempt to describe gravity at extremely small scales, near black holes or the moment of the Big Bang, the equations cease to make sense. This failure tells us that our understanding of space, time, and matter is incomplete. The Big Bang itself is the ultimate testing ground for the God equation. At the beginning of time, the universe was compressed into an unimaginably hot and dense state. Quantum effects and gravitational effects were equally important. Space and time were violently fluctuating. The laws of physics as we know them were fused into a single primordial framework. To understand the origin of the universe, we must understand physics at this scale. And that requires a theory that unites quantum mechanics and gravity. Einstein devoted the last 30 years of his life to this quest. After formulating general relativity, he sought a unified field theory that would incorporate electromagnetism and gravity into a single mathematical structure. He believed deeply that the universe was governed by elegant, harmonious laws.
Yet he died without achieving this goal. The God equation eluded even the greatest scientific mind in history. In the decades since Einstein's death, physicists have proposed many approaches to unification. Among them, one stands out for its mathematical elegance and scope: string theory. In string theory, the fundamental objects of the universe are not point-like particles, but tiny vibrating strings. Each mode of vibration corresponds to a different particle, much like different notes played on a violin string. Remarkably, one of these vibrations corresponds naturally to the graviton, the hypothetical quantum particle of gravity. String theory does something extraordinary. It automatically includes gravity within a quantum framework, resolving the central conflict between quantum mechanics and general relativity. Moreover, it suggests that the universe has more dimensions than the four we experience. In addition to 3 dimensions of space and 1 of time, string theory requires extra spatial dimensions that are curled up at incredibly small scales. These hidden dimensions shape the laws of physics we observe, determining the masses and properties of particles. Critics often point out that string theory has not yet been experimentally verified. That is true. The energies required to probe string-scale physics are far beyond our current accelerators. But history reminds us that theoretical breakthroughs often precede experimental confirmation by decades or even centuries. The existence of atoms, black holes, and gravitational waves were all predicted long before they were observed. The God equation may follow the same path. At its heart, the search for the God equation is not merely a technical exercise. It is a philosophical journey. It asks whether the universe is chaotic or orderly, accidental or inevitable. It challenges us to confront the deepest questions about existence, causality, and reality. If such an equation exists, it would imply that the universe is governed by necessity, that its laws could not have been otherwise. If it does not exist, then randomness and chance may lie at the foundation of everything.
As we embark on this exploration, we must be prepared to rethink our most basic assumptions about space, time, matter, and consciousness itself. The God equation, if discovered, would not merely complete physics, it would transform our understanding of reality. It would reveal whether the universe is a cosmic accident or a masterpiece of mathematical inevitability. This is why I call it physics' greatest mystery. To understand why the God equation has remained elusive, we must return to the man who first grasped its necessity with absolute clarity, Albert Einstein. After completing general relativity in 1915, Einstein achieved what many consider the greatest intellectual triumph in human history. He revealed that gravity is not a force in the traditional sense, but a manifestation of the curvature of space and time. Massive objects bend space-time, and objects move along those curves. With a few elegant equations, Einstein explained the motion of planets, the bending of light, and the structure of the cosmos. Yet for Einstein, this achievement was incomplete. He was deeply dissatisfied with the fragmented nature of physics. Electromagnetism existed as a separate theory, described by Maxwell's equations. Matter was explained through emerging quantum ideas that Einstein himself helped initiate, though he famously distrusted their probabilistic nature. Einstein believed that the universe must ultimately be governed by deterministic, unified laws. He was convinced that nature was elegant, simple, and mathematically coherent at its deepest level. For the last 30 decades of his life, Einstein pursued a unified field theory, a single mathematical framework that would merge gravity and electromagnetism.
He believed that by extending the geometry of space-time, perhaps into higher dimensions or more complex mathematical structures, all forces could be described as different aspects of geometry. In this vision, particles would emerge naturally as solutions to the equations rather than being inserted by hand. Matter itself would be geometry. Despite his brilliance, Einstein failed. His classical approach could not account for the strange behavior of the quantum world. Quantum mechanics, with its uncertainty, waveforms, and discrete energy levels, defied Einstein's intuition. He famously declared that God does not play dice with the universe. Yet experiment after experiment confirmed that quantum theory, however unsettling, was correct. The universe at small scales is governed by probability, not certainty. The failure of Einstein's unified field theory revealed a deeper truth. Classical physics alone is insufficient. The universe cannot be understood without quantum mechanics. At atomic and subatomic scales, nature behaves in ways that defy classical intuition. Particles exist in superpositions, occupying multiple states at once. Events occur probabilistically, governed by wave functions rather than deterministic trajectories. Any attempt to construct the God equation must incorporate these quantum principles at a fundamental level. The problem arises when we apply quantum mechanics to gravity. Quantum field theory treats forces as fields composed of particles exchanged between matter. Electromagnetism is mediated by photons, the strong force by gluons, the weak force by W and Z bosons. In principle, gravity should be mediated by a quantum particle called the graviton. But when we attempt to calculate quantum corrections to gravity, the mathematics becomes uncontrollable. Infinite quantities appear that cannot be renormalized or eliminated.
This failure is not a minor technical issue. It is a profound indication that our conception of space-time itself may be wrong. Quantum mechanics assumes a fixed background of space and time in which particles interact. General relativity, however, tells us that space-time is dynamic, flexible, and responsive to energy and matter. When we try to quantize gravity, these two assumptions clash violently. Space and time themselves begin to fluctuate, tearing apart the mathematical framework we rely on. At extremely small scales, near what we call the Planck length, space-time becomes turbulent and chaotic. It resembles a foaming sea, filled with microscopic black holes and quantum fluctuations. The smooth continuum described by Einstein dissolves into a quantum storm. Our current theories were never designed to operate under such conditions. The God equation must describe physics in this extreme regime where space, time, matter, and energy merge into a single entity. This realization forced physicists to explore radical new ideas. Perhaps space-time is not fundamental but emergent. Perhaps particles are not point-like but extended objects. Perhaps dimensions beyond our perception are essential to unification. These ideas were once considered speculative, even heretical, yet they arose not from imagination alone, but from the relentless demands of mathematical consistency. One of the key lessons from Einstein's failure is that unification cannot be achieved by incremental adjustments to existing theories. It requires a revolutionary framework. The God equation must be capable of explaining not only known forces, but also why quantum mechanics and gravity coexist at all. It must explain the origin of space-time itself, not merely its behavior under familiar conditions. Quantum mechanics also introduces another profound challenge: the role of the observer. In the quantum world, measurement plays a fundamental role in determining outcomes. The act of observation affects reality. This raises deep questions about the nature of reality itself.
Is the universe deterministic or probabilistic? Is consciousness a fundamental component of physical law? While the God equation may not directly answer these questions, it must be compatible with a universe in which probability and uncertainty are intrinsic features. As physicists grappled with these challenges, they realized that the Standard Model, despite its success, is incomplete. It contains too many arbitrary parameters, particle masses, coupling constants, and symmetries that appear to be chosen by hand. A true God equation would explain these values naturally, showing that they arise inevitably from deeper principles. The universe should not appear fine-tuned by coincidence. It should be the logical consequence of a single underlying structure. Einstein believed that simplicity was the hallmark of truth. He sought equations that were not only correct, but beautiful. The God equation, if it exists, must possess this quality. It must be concise, elegant, and inevitable. It must explain complexity as the unfolding of simple laws, much like the intricate patterns of a snowflake arise from basic principles of symmetry and thermodynamics. Today, we recognize that Einstein's dream was not misguided, it was incomplete. He lacked the mathematical tools and conceptual framework needed to unite quantum mechanics and gravity. Yet his intuition remains a guiding light. The universe is not a patchwork of unrelated laws. It is a coherent whole, governed by principles we are only beginning to glimpse. The failure to quantize gravity is not a defeat, but a clue. It tells us that space-time itself must be reimagined. It tells us that the God equation lies beyond conventional physics, waiting for a new language, a new perspective, and a new synthesis of ideas. The search continues, driven by the conviction that the universe, at its deepest level, is governed by a single unified law. To understand why physicists are convinced that a deeper theory must exist, we must examine the extraordinary success and the equally extraordinary limitations of quantum mechanics and the Standard Model. Quantum theory is without question the most accurate framework ever devised by the human mind. Its predictions have been verified to more decimal places than any other theory in science. It governs the behavior of atoms, molecules, radiation, and the fundamental particles that compose all matter. And yet, despite its precision, quantum mechanics leaves us with an unsettling sense of incompleteness. The Standard Model represents the culmination of this quantum framework. It unifies three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, into a single mathematical structure. It describes a zoo of particles: quarks, leptons, gauge bosons, and the Higgs boson. Each particle has specific properties, masses, and interactions, all encoded in elegant equations that have been tested with remarkable accuracy in particle accelerators around the world. Yet when I look at the Standard Model, I do not see the final word of physics. I see a beautiful but unfinished symphony. The model works, but it raises more questions than it answers. Why do particles have the masses they do? Why are there 3 generations of matter? Why do the forces have their particular strengths? These numbers appear arbitrary, inserted by hand rather than derived from deeper principles. A true God equation would not merely describe these values, it would explain them. One of the most compelling clues that the Standard Model is incomplete comes from the idea of force unification. At low energies, the electromagnetic force, the weak nuclear force, and the strong nuclear force appear distinct. But when we extrapolate the equations to extremely high energies, something remarkable happens. Their strengths begin to converge. They approach one another, hinting that at sufficiently high energies, near the beginning of the universe, they may merge into a single force. This convergence is not speculation, It is a direct consequence of quantum field theory. As energy increases, quantum fluctuations alter the effective strength of forces. This phenomenon, known as renormalization, reveals that the forces are dynamic, not fixed. The fact that three forces nearly unify at high energies suggests that they are manifestations of a deeper unified interaction. Gravity, however, stubbornly refuses to join them within the Standard Model framework.
Gravity's absence from the Standard Model is not an oversight. It is a reflection of a fundamental incompatibility. Quantum field theory assumes forces propagate within spacetime. General relativity tells us that spacetime itself is the force. This distinction is not cosmetic, it is profound. Gravity shapes the stage on which quantum processes unfold. Attempting to quantize gravity using the same methods as other forces leads to mathematical catastrophe. Another glaring omission in the Standard Model is dark matter. Astronomical observations reveal that ordinary matter accounts for only about 5% of the universe. The rest consists of dark matter and dark energy, mysterious components that shape the evolution of galaxies and cosmic expansion. The Standard Model cannot explain their nature. Any God equation worthy of the name must account for the dominant constituents of the universe. Quantum mechanics also introduces deep philosophical puzzles. At its core lies the wave function, a mathematical object that encodes probabilities rather than certainties. Until a measurement is made, particles exist in superpositions of states. This challenges classical notions of reality and causality. While quantum mechanics works spectacularly well, it leaves unanswered questions about the nature of measurement, the role of the observer, and the meaning of probability. These questions suggest that our understanding of reality is still provisional. Historically, whenever physics has encountered such conceptual tensions, a deeper theory has emerged. Classical mechanics could not explain the stability of atoms, leading to quantum theory. Newtonian gravity could not explain the behavior of objects at high speeds or strong gravitational fields, leading to relativity. Today, the tension between quantum mechanics and gravity signals the need for another revolution. The God equation is not an optional refinement, it is a necessity imposed by logic and experiment. The Higgs boson, discovered in 2012, offers another important clue. The Higgs field permeates all of space, giving mass to elementary particles. Without it, atoms, chemistry, and life itself would not exist. Yet the Higgs mass appears unnaturally small compared to the scales at which quantum gravity should become relevant. This so-called hierarchy problem suggests that new physics must stabilize the Higgs field. Once again, we are led beyond the Standard Model toward a deeper framework. Symmetry plays a central role in this search. Modern physics is built on the idea that symmetries dictate the laws of nature. The Standard Model is based on internal symmetries that govern particle interactions. Unification theories seek larger, more encompassing symmetries that reduce complexity. The God equation would represent the ultimate symmetry, one from which all others emerge. In this vision, particles and forces are not fundamental. They are expressions of symmetry breaking as the universe cools from its primordial state. Despite its successes, quantum mechanics leaves gravity out in the cold. This exclusion is unacceptable if we believe the universe is governed by a single set of laws. The unification of forces is not merely an aesthetic preference, it is a historical pattern supported by overwhelming evidence. The God equation must complete this pattern by incorporating gravity into the quantum framework. As physicists probe deeper into matter and energy, they encounter boundaries that cannot be crossed without new ideas. Particle accelerators approach practical limits. Observations of the cosmos reveal phenomena that defy explanation. These boundaries are not failures, they are signposts. They tell us where our current theories end and where the God equation must begin. In the search for this ultimate law, we are driven not only by curiosity, but by necessity. The universe demands consistency. Nature does not operate with incompatible rules at different scales. The apparent fragmentation of physics is a reflection of our limited understanding, not of reality itself. Beneath the surface complexity lies a deeper order, waiting to be revealed. The Standard Model and quantum mechanics have taken us far, but they have also shown us their limits. The next step requires a theory that transcends them, a framework capable of unifying all forces, explaining all constants, and revealing the fundamental architecture of reality. This is the promise of the God equation, and this is why physicists continue the search with unwavering determination. When physicists finally confronted the fact that gravity refuses to be quantized using conventional methods, it became clear that a radical rethinking of nature was required. The idea that particles are point-like objects, infinitely small dots with no internal structure, had served us well, but it also led directly to mathematical infinities when gravity entered the picture. At this impasse, a revolutionary idea emerged. Perhaps the fundamental constituents of reality are not points at all, but tiny vibrating strings. String theory proposes that every particle we observe, electrons, quarks, photons, even the graviton, is actually a different vibration of an incredibly small, one-dimensional string. Just as different musical notes arise from different vibrational modes of a violin string, the properties of particles arise from the way these strings vibrate. Mass, charge, and spin are not intrinsic attributes, they are manifestations of vibration. In this picture, the universe is not composed of particles, but of music. This simple shift has profound consequences. When strings interact, they do not collide at sharp points. Instead, they merge and split smoothly, spreading interactions over a finite region. This softness eliminates the catastrophic infinities that plague quantum gravity. Gravity emerges naturally from string theory not as an added feature, but as an inevitable consequence. The graviton appears automatically as one of the allowed vibrational states. For the first time, a quantum theory of gravity becomes mathematically consistent. What astonished physicists was that string theory demanded something even more radical: extra dimensions of space. The equations simply do not work unless spacetime has more than the familiar 3 dimensions of space and 1 of time. In most versions of string theory, the universe has 10 or 11 dimensions. The extra dimensions are not visible because they are compactified, curled up into shapes so small that they evade direct detection. This idea may sound fantastical, but it has deep mathematical roots. If the extra dimensions are arranged in specific geometric forms, known as Calabi-Yau manifolds, the equations of string theory become consistent and predictive. Remarkably, the shape of these hidden dimensions determines the properties of particles in our observable universe. The masses of particles, the strengths of forces, and the patterns of symmetry all depend on the geometry of dimensions we cannot see. In this way, string theory offers a stunning realization of Einstein's dream. Matter is geometry. Forces are geometry. Even the constants of nature may be encoded in the shape of extra dimensions. The God equation in this framework is not a single line written on a chalkboard, but a master principle from which all physical laws emerge as consequences of geometry and symmetry. String theory also introduces a powerful concept known as dualities. Dualities reveal that theories which appear radically different are, at a deeper level, mathematically equivalent. A strongly interacting system in one description may be equivalent to a weakly interacting system in another. This means that our intuition about space, time, and matter can be deeply misleading. Reality may have multiple equivalent descriptions, each revealing different aspects of the same underlying truth. One of the most profound examples is holography. According to the holographic principle, the physics within a volume of space can be described entirely by information encoded on its boundary. This idea emerged from studies of black holes and string theory. It suggests that the universe itself may be a hologram, with three-dimensional reality emerging from more fundamental two-dimensional laws. Space, once again, appears to be emergent rather than fundamental. Black holes provide a critical testing ground for these ideas. They represent the ultimate collision between quantum mechanics and gravity. String theory has successfully explained the microscopic origin of black hole entropy, showing that the entropy arises from the vast number of ways strings and branes can arrange themselves. This achievement is one of the strongest pieces of evidence that string theory captures something essential about quantum gravity. Yet, string theory is not without controversy. Critics argue that it lacks direct experimental verification. The energies required to probe string-scale physics are far beyond the reach of current particle accelerators. The theory also appears to allow an enormous number of possible solutions, each corresponding to a different universe with different physical laws. This so-called landscape problem challenges the idea that string theory uniquely predicts our universe. Rather than weakening the theory, this vast landscape may reveal a deeper truth. It suggests that our universe is one of many possible solutions, each governed by the same underlying equations. The God equation may not specify a single universe, but a space of possible universes. The laws of physics we observe may be environmental, determined by the region of the multiverse we inhabit. This idea forces us to confront uncomfortable questions. Are the constants of nature uniquely determined, or are they selected by cosmic evolution? Is the universe fine-tuned for life by design, necessity, or chance? While string theory does not answer these questions definitively, it provides a framework in which they can be meaningfully explored.
Extra dimensions also open new possibilities for cosmology. They may explain the weakness of gravity, the nature of dark matter, or the behavior of the early universe. In some scenarios, our universe is a three-dimensional membrane, or brane, floating in a higher dimensional space. Other universes may exist nearby, separated from us by dimensions we cannot access. Gravity alone may leak between these branes, offering new explanations for cosmic phenomena. What is most compelling about string theory is not that it has all the answers, but that it unifies ideas that once seemed irreconcilable. Quantum mechanics, gravity, geometry, and symmetry come together in a single mathematical framework. The theory suggests that at the deepest level, the universe is not made of matter or energy, but of information and vibration. If the God equation exists, string theory brings us closer than ever before. It offers a language capable of describing the birth of the universe, the behavior of black holes, and the quantum structure of spacetime. It challenges our intuition and expands our imagination, reminding us that reality is far stranger and more beautiful than we ever suspected. As string theory evolved, physicists uncovered a surprising and deeply unsettling truth. What we once believed to be 5 distinct string theories were not competing ideas at all. They were different faces of a single, more profound framework. This realization gave rise to what we now call M-theory, a higher dimensional theory that unifies all versions of string theory into one coherent structure. In this picture, strings are no longer fundamental objects. Higher dimensional entities known as membranes or brains take center stage. M-theory exists naturally in 11 dimensions, pushing the concept of extra dimensions even further. These dimensions are not mere mathematical artifacts, they are essential to the consistency of the theory. In this framework, strings emerge as one-dimensional slices of higher-dimensional membranes. The universe itself may be a 3-dimensional brain embedded within a higher-dimensional space, known as the bulk. This idea radically reshapes our understanding of reality. What is truly astonishing is that gravity, unlike other forces, is free to propagate through the higher-dimensional bulk. This may explain why gravity is so weak compared to other forces. It is diluted across extra dimensions. The God equation in this context is not confined to our observable universe. It governs a vast higher dimensional reality of which our cosmos is only a small part. M-theory also provides a natural setting for the multiverse. The equations allow for an enormous number of stable solutions, each corresponding to a different universe with its own physical laws. These universes may differ in their number of dimensions, particle spectra, force strengths, and even the nature of time itself. Our universe may be one bubble in a cosmic foam of universes.
This idea challenges a long-standing assumption in physics that the laws of nature are unique and inevitable. Instead, they may be contingent. The God equation may not dictate a single outcome, but a vast landscape of possibilities. The universe we inhabit could be selected by environmental factors, such as the ability to form complex structures and observers. This perspective transforms fine-tuning from a mystery into a statistical consequence. The multiverse concept gains further support from cosmology. Inflationary theory suggests that the early universe underwent a rapid expansion driven by high energy fields. In some versions of inflation, this process never completely ends. Instead, it continually spawns new regions of space, each with its own physical properties. These regions become separate universes, causally disconnected from one another. In this picture, the Big Bang was not the beginning of everything, but the birth of our local region of spacetime. Other universes may exist beyond our observable horizon, governed by the same fundamental equations, but manifesting different laws. The God equation, therefore, describes not just our universe, but the entire multiverse. Critics argue that the multiverse is unscientific because it may be impossible to test directly. Yet physics has always confronted realities beyond direct observation. Quarks, atoms, and curved spacetime were once invisible abstractions. What matters is not visibility, but explanatory power and mathematical consistency. If the multiverse emerges naturally from a theory that explains known phenomena, it deserves serious consideration. M-theory also sheds light on one of the deepest puzzles in cosmology, the cosmological constant. Observations reveal that the universe is accelerating, driven by dark energy.
The measured value of this energy is extraordinarily small compared to theoretical predictions. Within the multiverse framework, different universes may have different values of the cosmological constant. We find ourselves in a universe where the value is small enough to allow galaxies, stars, and life to form. This does not diminish the power of physics, it reframes it. The God equation may define a probability distribution over possible universes, rather than a single deterministic outcome. The laws we observe are not arbitrary, but selected from a vast ensemble by cosmic evolution and anthropic constraints. M-theory also sheds light on the origin of space-time itself. In certain formulations, space and time are not fundamental ingredients. They emerge from more primitive entities, governed by quantum principles. This suggests that the beginning of the universe may not be a singularity in the traditional sense. Instead, it may be a transition between different phases of a deeper reality. The implications of this idea are staggering. Time may have existed before the Big Bang in some form. The universe may undergo cycles of birth, evolution, and transformation across different dimensions. The God equation may describe a timeless structure from which all possible histories emerge. Despite its elegance, M-theory remains incomplete. We do not yet possess its final equations. Much like early quantum mechanics, we understand its fragments and symmetries, but not its full formulation. Yet the clues are compelling. Every path toward unification seems to converge on higher dimensions, extended objects, and emergent spacetime.
Einstein once sought a single equation that would reveal the mind of God. What we have discovered instead is something even more profound, a framework that may describe not just one universe, but all possible universes. The God equation, if it exists, is not merely a description of reality, it is a generator of realities. This realization forces us to confront the limits of human understanding. We are small creatures in a vast cosmic landscape, attempting to comprehend laws that operate far beyond our everyday experience. Yet history shows that the universe is comprehensible. Each generation peels back another layer of mystery, revealing deeper order beneath apparent chaos. The multiverse is not the end of science, but a new beginning. It expands the scope of physics and challenges us to develop new methods of testing, reasoning, and understanding. The God equation may be subtle, complex, and elusive, but it is not beyond reach. It is written into the fabric of reality itself, waiting for us to learn how to read it. If there is any object in the universe that forces us to confront the deepest laws of nature, it is the black hole. Black holes are not merely exotic astrophysical curiosities. They are theoretical laboratories where gravity, quantum mechanics, and thermodynamics collide. They push our theories to their limits and reveal cracks in our understanding of reality. Any true God equation must explain black holes completely, without contradiction. According to general relativity, a black hole forms when a massive star collapses under its own gravity, creating a region of spacetime so strongly curved that nothing, not even light, can escape. At its center lies a singularity, a point of infinite density where the equations of physics break down. Surrounding it is the event horizon, a boundary beyond which information appears to be lost forever. Quantum mechanics, however, refuses to accept this conclusion. One of its most sacred principles is that information is conserved. Information may be scrambled, hidden, or transformed, but it can never be destroyed. This leads to a profound paradox. If information falls into a black hole and disappears at the singularity,
quantum mechanics is violated. If it somehow escapes, general relativity is violated. This conflict is known as the black hole information paradox, and it strikes at the heart of modern physics. The paradox became even sharper when Stephen Hawking discovered that black holes are not truly black. Quantum effects near the event horizon cause black holes to emit radiation, now known as Hawking radiation. Over immense timescales, a black hole can evaporate completely, leaving behind only thermal radiation. The troubling implication is that this radiation appears to carry no information about what fell into the black hole. Information seems to be erased from the universe. This result was shocking. It suggested that quantum mechanics itself might be incomplete. For decades, physicists debated whether information is truly lost or merely hidden. The resolution of this paradox has driven some of the most profound discoveries in theoretical physics and has provided powerful clues about the nature of the God equation.
One key insight came from studying black hole entropy. Jacob Bekenstein showed that black holes possess entropy proportional to the area of their event horizon, not the volume of the region they contain. This was a radical departure from conventional thermodynamics, where entropy scales with volume. The implication was staggering. The information content of a region of space may be encoded on its boundary. This idea led to the holographic principle. Just as a two-dimensional hologram can encode a three-dimensional image, the universe itself may encode its physics on lower-dimensional boundaries. In this view, our three-dimensional world could be a projection of more fundamental laws defined on a two-dimensional surface. Space, once again, appears to be emergent rather than fundamental. String theory provided strong support for this idea. In certain formulations, a gravitational theory in higher dimensions is mathematically equivalent to a quantum field theory without gravity in lower dimensions. This correspondence, known as gauge-gravity duality, demonstrates that gravity and space-time can emerge from more fundamental non-gravitational physics. The God equation, therefore, may not be written in terms of space and time at all. The implications of holography are profound. It suggests that the universe is fundamentally informational. Matter, energy, space, and time emerge from underlying patterns of quantum information. Reality, at its deepest level, may be composed not of particles or fields, but of bits of information and their relationships. This perspective reshapes our understanding of black holes. Information that falls into a black hole may be encoded on the event horizon itself, spread across its surface in a highly scrambled form. As the black hole evaporates, this information is slowly released through subtle correlations in Hawking radiation. Information is not destroyed, it is transformed. While the precise mechanism remains under active investigation, most physicists now believe that information is conserved. This conclusion preserves the integrity of quantum mechanics and suggests that space-time geometry must adjust itself in ways we do not yet fully understand. The God equation must reconcile these ideas seamlessly, without paradox or inconsistency. Holography also offers new insights into the nature of space-time itself. If space-time emerges from quantum entanglement, then geometry is not fundamental, it is a consequence of information flow. Distances, curvature, and even time may emerge from patterns of entanglement among underlying degrees of freedom. This represents a complete reversal of our classical intuition. In this view, the fabric of space-time resembles a vast quantum network. Connections between nodes represent entanglement. The strength and pattern of these connections determine the shape of space-time.
When entanglement changes, geometry changes. Gravity becomes a manifestation of information dynamics rather than a fundamental force. Black holes, once feared as destroyers of information, now appear as the ultimate storage devices. They compress vast amounts of information into a minimal surface area. Understanding how this information is encoded and released may provide the final key to unifying quantum mechanics and gravity. These ideas also force us to rethink the Big Bang. If spacetime emerges from quantum information, then the beginning of the universe may not be a singularity in the traditional sense. Instead, it may represent a phase transition in an underlying informational structure. Time itself may emerge from more primitive, timeless laws.
The God equation, therefore, may not resemble a conventional equation at all. It may be a principle governing information, entanglement, and emergence. Space and time would then be secondary concepts, useful approximations rather than fundamental ingredients. Einstein once sought a theory written in the language of geometry. We are now discovering that geometry itself may be written in the language of information. This is not a betrayal of Einstein's vision, but its fulfillment at a deeper level. The universe is still governed by elegant laws, but those laws may be more abstract than we ever imagined. Black holes have transformed from cosmic monsters into guides. They illuminate the path toward the God equation by revealing where our theories fail and how they must evolve. In confronting the paradoxes of black holes, we are forced to confront the nature of reality itself. The resolution of these mysteries will not only complete our understanding of black holes, it will redefine our understanding of the universe, showing us that space, time, and matter are emergent phenomena arising from deeper informational principles. And in doing so, it will bring us closer than ever to the ultimate goal of physics, a single coherent description of all that exists. If black holes teach us about the structure of reality, the Big Bang teaches us about its origin. The universe began in a state of extraordinary density and temperature, a singular moment when space, time, matter, and energy were fused into a single entity. Understanding this origin is one of the greatest challenges in physics, and it is precisely here that the God equation may finally reveal its power. The Big Bang is not merely a point in time, it is a window into physics at its most extreme. At scales near the Planck length, quantum fluctuations dominate and classical descriptions of space and time cease to exist. Gravity and quantum mechanics are equally important, yet they are mathematically incompatible under conventional frameworks. To understand the birth of the universe, we require a theory that seamlessly unites these two pillars. This is precisely the promise of the God equation. Cosmologists have made enormous progress in mapping the early universe. Observations of the cosmic microwave background, the afterglow of the Big Bang, reveal tiny fluctuations in density that seeded the formation of galaxies. Inflationary theory suggests that the universe underwent an exponential expansion in its first moments, stretching quantum fluctuations across cosmic scales. Yet the mechanism behind inflation remains speculative. Only a complete theory of quantum gravity could explain why inflation occurred and why the universe emerged in the precise way that allowed galaxies, stars, and life to form. The God equation, in principle, could answer one of the oldest philosophical questions: why is there something rather than nothing? Conventional physics begins with a set of initial conditions and evolves them forward in time. But the deeper question is why these initial conditions exist at all. Why does the universe have laws, symmetries, and constants? Why is there a cosmos instead of empty void? Some theories suggest that the universe spontaneously emerged from a quantum vacuum. In quantum mechanics, empty space is never truly empty. It is filled with fluctuations, virtual particles that appear and disappear in accordance with Heisenberg's uncertainty principle. On the smallest scales, energy can briefly materialize into matter, and under certain conditions, an entire universe could nucleate from such a fluctuation. If the God equation governs these processes, it would not only describe the universe's evolution, but explain its very existence. Inflation and quantum cosmology also imply the possibility of multiple universes. If the universe can spontaneously arise from a vacuum, then it may do so repeatedly, creating a multiverse. Each universe could have different physical laws, different constants, and even different numbers of dimensions. The God equation would provide a unifying principle that governs all possible universes, explaining why our universe possesses the specific properties we observe. One of the most fascinating consequences of the God equation is that it may render the concept of the singularity obsolete. Instead of a point of infinite density, the beginning of the universe could be a phase transition in a pre-existing quantum structure. Space and time would emerge naturally from the underlying laws, much as water emerges from hydrogen and oxygen atoms. The beginning of the cosmos, then, is not a paradox, but a natural consequence of a deeper theory. Entropy plays a crucial role in this story. The second law of thermodynamics tells us that the universe evolves from states of low entropy to high entropy. Yet the early universe was astonishingly ordered, with extremely low entropy compared to what one might expect. Why did it begin in such a finely tuned state? A complete God equation could explain this initial order as a necessary outcome of fundamental principles rather than a mere coincidence. The God equation would also unify the microcosm and the macrocosm. Quantum fluctuations in the earliest moments of the universe became the seeds of galaxies and cosmic structure. Gravity amplified these tiny irregularities, shaping the vast web of stars and galaxies we observe today. From the smallest quanta to the largest clusters of galaxies, all of physics would be encoded in a single, elegant framework. This theory could also explain the observed acceleration of the universe, driven by dark energy. Why does the cosmos expand at the rate it does? Why is the dark energy density so small compared to theoretical expectations? These questions are intimately connected to the initial state of the universe. The God equation would reveal the deep connection between the birth of the cosmos and its ongoing evolution. Moreover, the God equation could clarify the nature of time itself. Is time fundamental or emergent from deeper laws? In certain quantum gravity frameworks, time arises as a parameter describing correlations between physical systems rather than as an independent backdrop. If this is correct, then the flow of time, the sequence of cause and effect, and even the directionality implied by entropy emerge from the underlying structure described by the God equation. The quest for the God equation also bridges physics and philosophy. It challenges us to ask not only how the universe operates, but why it exists at all. Why are there laws of nature? Why are the constants tuned to allow the formation of galaxies, stars, planets, and ultimately life? A complete theory would provide answers to these questions, demonstrating that the cosmos is not arbitrary, but a necessary consequence of a deeper mathematical reality. In contemplating the Big Bang, we also confront the unity of space, time, and matter. At its inception, these elements were inseparable. They emerged as a coherent structure only as the universe cooled and expanded. The God equation would describe this emergence, revealing how the fundamental constituents of reality, energy, space, time, and information are intertwined from the very beginning. Finally, the God equation may have implications for consciousness itself. If the universe is fundamentally informational, as suggested by holography and quantum entanglement, then consciousness may be an emergent property of the universe's informational structure. While this remains speculative, the idea opens the door to a unified understanding of mind and matter within the same framework. The ultimate laws of physics may not only describe the cosmos, but also the processes that give rise to awareness within it. In essence, the God equation represents the culmination of humanity's centuries-long quest to understand reality. It promises to answer the deepest questions: why the universe exists, why it has the laws it does, and why it allows for the complexity we observe. It unites the infinitely small and the infinitely large, the microcosm and the macrocosm, the quantum and the cosmic into a single coherent vision. To find this equation is to read the mind of the cosmos itself. Having explored the theoretical landscape of the God equation, one naturally asks, what would its discovery mean for humanity? Beyond satisfying our deepest intellectual curiosity, the God equation carries profound implications: technological, philosophical, and existential. The mastery of a complete understanding of nature could revolutionize civilization in ways we can scarcely imagine. From a technological perspective, the God equation would provide access to the fundamental mechanisms of the universe. Currently, we manipulate matter and energy indirectly, guided by approximate models and engineering ingenuity. With a full understanding of the underlying laws, it might become possible to control phenomena that today seem miraculous. We could engineer matter at its most fundamental level, creating materials with properties beyond imagination, designing energy sources that rival the output of stars, and perhaps even manipulating space-time itself. Imagine technologies derived from a complete quantum gravity framework, concepts that today belong to science fiction. Warp drives, stable wormholes, or near-limitless energy sources would no longer be forbidden by our understanding of physics. The God equation would offer a blueprint revealing which configurations of matter and energy are permissible and which are forbidden by the universe's fundamental principles. It would shift humanity from being passive observers of the cosmos to active participants in its design. Philosophically, the implications are equally staggering. The God equation would answer questions that have haunted thinkers for millennia. Why is there order rather than chaos? Why do the laws of nature allow for life and consciousness? By providing a single framework encompassing all phenomena, the God equation would suggest that the universe is not a random accident, but a coherent, necessary manifestation of deeper mathematical truth. It would fulfill Einstein's intuition that nature is profoundly simple and beautiful at its core. Such a discovery would also reshape our understanding of life and consciousness. If the universe is fundamentally informational, then biological systems, minds, and perhaps even artificial intelligence could be seen as emergent structures governed by the same underlying laws. We might develop the ability to predict, simulate, or even create complex systems, potentially merging the realms of physics, biology, and cognitive science into a single unified framework. The societal impact of such a discovery cannot be overstated. Humanity would gain a profound sense of perspective, understanding its place within a vast, interconnected cosmos. We would see that our existence is not arbitrary, but a natural consequence of deep universal laws. The God equation would provide a cosmic narrative, linking the smallest quanta to the largest structures, from the subatomic particles within our bodies to the galaxies spinning across the universe. Our sense of unity with the cosmos would deepen. Ethical and philosophical questions would inevitably arise. If we possess the knowledge to manipulate matter, energy, and space-time on fundamental scales, what responsibilities accompany such power?
How would societies manage technologies capable of reshaping the environment, the human body, or even reality itself? The God equation would demand not only scientific insight, but moral discernment, calling upon humanity to evolve alongside our understanding of the cosmos. Moreover, the discovery of the God equation could resolve enduring paradoxes that have puzzled physicists for decades. It would unify quantum mechanics with general relativity, showing how the laws governing the infinitely small and the infinitely large are consistent and interdependent. It would explain the nature of black holes, the origin of the universe, the behavior of fundamental particles, and the properties of spacetime itself. In doing so, it would reveal a cosmos governed by necessity, not accident. On a more personal level, the God equation would profoundly influence human thought and imagination. Artists, philosophers, and scientists would gain access to a new lens through which to view reality. Our myths, metaphors, and stories would be informed by a deeper understanding of the universe's structure. The boundary between science and philosophy would blur, as knowledge of the fundamental laws inspire a new human culture of exploration and meaning. The implications extend even to questions of artificial intelligence and consciousness. If reality is informational at its core, and if consciousness arises from complex informational patterns, then the God equation could guide us in creating artificial minds capable of understanding and interacting with the universe in unprecedented ways. We might even imagine the possibility of simulating entire universes, exploring their laws, and observing emergent phenomena in controlled computational environments. In this sense, the God equation could become the ultimate tool for understanding reality both inside and outside ourselves.
Furthermore, the God equation would provide clarity on the multiverse. We could predict which universes are physically possible, which laws emerge naturally, and which scenarios are forbidden. This would transform our understanding of cosmic evolution, fine-tuning, and the anthropic principle. The apparent coincidences that allow life to exist in our universe would no longer be mysteries. They would be predictable consequences of deep underlying principles. In education and science, the discovery would revolutionize how we teach and explore physics. Students could learn not only the equations that govern matter and energy, but also their derivations from a single unifying principle. The God equation would provide the ultimate roadmap, enabling generations of physicists to pursue questions that were previously inaccessible. Research would shift from piecemeal exploration to systematic investigation, guided by the structure of the universe itself. Ultimately, the God equation represents more than science. It is the culmination of humanity's quest to comprehend reality. It embodies the hope that the universe is intelligible, coherent, and beautiful. It reminds us that curiosity and reason can penetrate the deepest mysteries, transforming wonder into understanding. For anyone who has gazed at the night sky and wondered why the cosmos exists in precisely the way it does, the God equation offers a tantalizing answer. The universe is the manifestation of a single, elegant, inevitable law. Of course, the God equation is not yet fully discovered. We are still assembling the pieces, exploring string theory, M theory, holography, and quantum gravity. But each step brings us closer. Each insight, whether from black holes, cosmic microwave background observations, particle accelerators, or mathematical breakthroughs, illuminates the path. The quest is ongoing, and it is one of the most exciting and profound endeavors in human history. The journey toward the God equation exemplifies the power of human imagination, logic, and persistence. It demonstrates that despite our smallness in the cosmos, our intellect can approach the very foundations of existence.
When we finally decipher the ultimate law of nature, we will not only know the mechanics of the universe, we will understand the reasons for its order, its beauty, and perhaps even the place of consciousness within it. That is the promise of the God equation, physics' greatest mystery and its most profound aspiration. As we approach the final frontier of physics, a profound question emerges. Can finite human minds truly comprehend the God equation? History shows that our understanding of the universe grows incrementally, punctuated by leaps of insight. Newton revealed the mathematics of motion and gravity. Maxwell unified electricity and magnetism. Einstein revolutionized our conception of space and time. Yet each breakthrough also exposed deeper layers of mystery. The God equation may represent the ultimate leap, but it also tests the limits of human cognition. Mathematics is the language of the universe, and mathematical beauty often guides physicists toward truth. Equations that are elegant, symmetrical, and minimal tend to describe reality with astonishing accuracy. Einstein, Dirac, and others relied on aesthetic principles to discover fundamental laws. It is plausible that the God equation will be mathematically beautiful in a way that transcends our current imagination, a concise, inevitable formulation from which all known physics emerges.
Yet beauty alone does not guarantee comprehension. The God equation may involve structures so abstract and high-dimensional that direct intuition fails. Just as early humans could not visualize four-dimensional space, we may struggle to grasp the full implications of 11-dimensional geometries, holographic entanglement, or emergent spacetime. Nevertheless, mathematics allows us to navigate such terrains. Through symbols, logic, and proof, we can manipulate concepts that defy sensory intuition. Another limit comes from computational complexity. Even if we have the correct equations, extracting predictions may require resources beyond our current capabilities. The God equation may encode an enormous amount of information governing every particle interaction, black hole formation, and cosmic fluctuation. Direct computation may be impossible, but approximations, simulations, and statistical methods could allow us to extract meaningful understanding without solving the equation in its entirety. Philosophically, the discoverability of the God equation raises profound questions. Is there a single, unique law that governs the universe, or is there a landscape of possible laws from which our reality emerges? M-theory suggests a metaverse of possibilities, each consistent with the underlying principles. In this view, the God equation describes a meta-law, a structure governing the space of all possible universes. Our universe is a realization within that space. Discovering the God equation may therefore require not only understanding our cosmos, but understanding the broader landscape of possibilities. Human cognition itself is limited by biological constraints. Our brains evolved to navigate a three-dimensional environment, hunt for survival, and recognize patterns. Yet physics demands abstraction far beyond these evolutionary imperatives. To bridge the gap, we rely on mathematics, symbolic reasoning, and collaborative knowledge. Generations of physicists have expanded our cognitive reach, using logic and experiment to probe realms inaccessible to intuition. The God equation represents the ultimate extension of this process. Interestingly, the God equation may also illuminate why the universe is comprehensible to us at all. If physical laws were chaotic, inconsistent, or incomprehensible, intelligent observers could not exist. The fact that humans can understand physics, at least in part, may reflect a deep correspondence between the structure of reality and the logic of cognition.
Mathematical patterns, symmetry, and consistency are not only features of the cosmos, they are prerequisites for consciousness capable of observing and reasoning about it. The pursuit of the God equation also exemplifies the interplay between knowledge and mystery. Every discovery uncovers new layers of complexity. Quantum mechanics challenged classical determinism. General relativity challenged Newtonian absolutes. String theory and holography challenge our concepts of space, time, and reality. The God equation may finally unify these insights, yet even then, the universe may retain inexhaustible richness. Understanding a law does not exhaust the phenomena it governs. The depth of reality may always exceed our grasp. This realization is both humbling and inspiring. Humbling because it reminds us of our cognitive limitations and the vastness of the cosmos. Inspiring because it demonstrates the power of reason and imagination to extend human understanding far beyond immediate perception. The God equation is not merely a scientific goal, it is a symbol of humanity's quest for meaning, order, and comprehension in a universe that is often counterintuitive and immense.
Mathematical abstraction allows us to see beyond sensory limitations. Concepts like extra dimensions, quantum entanglement, and holography might seem fantastical, yet mathematics makes them precise and manipulable. Even if the God equation operates in a regime beyond everyday experience, its consequences can manifest in observable phenomena, from particle interactions in accelerators to the structure of cosmic background radiation. This connection between abstract law and empirical observation is the hallmark of physics at its deepest level. Another profound aspect of the God equation is its unifying power. It may merge disparate branches of knowledge: quantum field theory, general relativity, thermodynamics, information theory, cosmology, and perhaps even consciousness. Historically, unification has yielded tremendous insight. Maxwell's equations unified electricity and magnetism. The electroweak theory unified electromagnetism and the weak force. Each unification simplified our understanding and revealed hidden connections. The God equation represents the ultimate unification, revealing that the multiplicity of physical phenomena is an expression of a single underlying law. Yet even as we approach this pinnacle, we must recognize the possibility that full comprehension may elude us. The God equation may contain infinite subtlety or involve structures so abstract that they challenge human intuition. Some aspects may be accessible only through indirect evidence, approximation, or analogy. Nonetheless, the pursuit itself enriches human knowledge, guiding us toward deeper conceptual and mathematical sophistication. Finally, the quest for the God equation reflects a uniquely human aspiration: the desire to know, to unify, and to find meaning in the cosmos. It embodies the intersection of science, philosophy, and even spirituality, without appealing to supernatural explanations. It is a journey that celebrates reason, creativity, and collaboration. Whether or not we ever write down the final equation in a single line, the pursuit will continue to illuminate the fundamental structure of reality and our place within it. In conclusion, the God equation is more than a goal. It is a narrative of human curiosity and intellectual courage. It challenges us to expand our mathematical imagination, refine our observational skills, and embrace both the known and the unknown. It reminds us that the universe is coherent, discoverable, and profoundly beautiful, yet infinitely rich. The pursuit of the God equation unites us with the grand adventure of science itself, the relentless quest to understand why the cosmos exists, how it operates, and why we, as conscious observers, are part of its magnificent tapestry. As we reach the culmination of our journey through the universe of ideas, it is time to synthesize what we have learned.
The God equation is not a single formula in the traditional sense. It is the unifying principle that explains why the universe exists, why its laws are what they are, and how all phenomena, from the tiniest quark to the largest galaxy, emerge from a coherent framework. It represents the apex of human understanding, the final frontier of theoretical physics. We began by examining the Standard Model and the extraordinary precision it offers in describing fundamental particles and forces. Yet even its brilliance revealed incompleteness. Gravity remained outside its purview, and the constants of nature appeared arbitrary. The unification of forces at high energies hinted at a deeper order, suggesting that matter, energy, and interaction were different expressions of the same underlying reality. String theory and M-theory expanded this vision by proposing that the building blocks of reality are not point-like particles, but vibrating strings and higher-dimensional membranes. These tiny oscillating objects encode the properties of all known particles, and the extra dimensions they inhabit determine the laws and constants of our universe. The God equation in this framework is a geometric, informational, and vibrational principle from which all physics flows naturally. The holographic principle and the study of black holes pushed us further, showing that reality itself may be fundamentally informational. Space and time may emerge from patterns of quantum entanglement. Gravity may arise from the dynamics of information, and the universe may be a holographic projection of deeper, higher-dimensional laws. Black holes, once seen as destroyers of information, are now understood as gateways to understanding how information, entropy, and geometry interweave to form the fabric of reality. Cosmology provides yet another layer of insight. The Big Bang, inflation, and the multiverse suggest that our universe is only one of many realizations of the underlying laws described by the God equation. The initial conditions, fine-tuned constants, and seemingly improbable order are consequences of deeper symmetries and principles that govern the emergence of universes. The God equation is not merely a description of what is, it is a generative principle, creating all possible realities consistent with fundamental rules. The philosophical implications are profound. Understanding the God equation illuminates why the universe is comprehensible, why it is ordered, and why life and consciousness arise. If the cosmos is informational at its core, consciousness may emerge naturally from complex informational structures, linking mind and matter within the same ultimate framework. Physics and awareness, observation and existence become intertwined expressions of the same underlying law. Moreover, the God equation exemplifies the pattern of scientific unification that has guided physics for centuries. From Newton's mechanics to Maxwell's electrodynamics, from quantum mechanics to general relativity, we have witnessed the gradual consolidation of apparently disparate phenomena under simpler, universal principles. The God equation is the final step in this journey, a comprehensive synthesis that unites forces, particles, space-time, and information into a single, coherent narrative. Its discovery would revolutionize technology, allowing humanity to manipulate matter, energy, and perhaps even space-time in ways that today seem miraculous. It would empower us with predictive understanding of the cosmos on scales from the subatomic to the multiversal. It would deepen our philosophical and ethical engagement with reality, challenging us to wield such knowledge responsibly. The God equation is both a scientific achievement and a human story, reflecting our drive to comprehend, explore, and flourish within the universe.
Yet even as we aspire to discover it, the God equation reminds us of the limits and beauty of human understanding. The universe may contain complexities that transcend direct intuition, requiring mathematics, abstraction, and collaboration to navigate. The pursuit itself enriches us, expanding our conceptual horizons and deepening our appreciation of the cosmos. The quest is as significant as the answer, a testament to the power of reason, imagination, and collective inquiry. In the end, the God equation is more than physics. It is a lens through which to view existence itself. It reveals that the cosmos is not arbitrary, chaotic, or incomprehensible. It is ordered, unified, and intelligible, governed by principles that we, through curiosity and intellect, can gradually uncover. It connects the infinitely small to the infinitely large, the quantum to the cosmic, the mathematical to the material, and perhaps mind to matter. For anyone who has gazed at the night sky, contemplated the complexity of life, or marveled at the mysteries of existence, the God equation represents the ultimate promise that beneath all phenomena lies a single elegant truth. Whether fully discoverable or only partially accessible, the God equation embodies humanity's relentless pursuit of understanding, a journey that is both scientific and profoundly human. It is the culmination of our search to read the mind of the cosmos and to glimpse at last the logic, harmony, and beauty that underlies everything we observe. The God equation is not just a scientific goal, it is a metaphor for the unity of knowledge, the interconnection of phenomena, and the potential of human intellect. It is the ultimate expression of the belief that the universe is comprehensible, that patterns and symmetries exist at the deepest level, and that through reason and imagination we can grasp the principles that govern all reality. And in that grasp lies both the awe and the responsibility of being conscious participants in a universe that is as elegant as it is vast. In conclusion, physics's greatest mystery, the God equation, is more than a quest for equations or constants. It is a journey to unify forces, understand emergence, reconcile quantum mechanics with gravity, and illuminate the informational and structural nature of reality. It is a vision that links the Big Bang to black holes, particles to galaxies, and consciousness to the cosmos. It is, ultimately, the story of human curiosity reaching toward the mind of God, seeking to understand not only how the universe works, but why it exists, why it is structured as it is, and why, against all odds, we find ourselves capable of understanding it at all. This pursuit continues to inspire generations of physicists, mathematicians, and thinkers, reminding us that the universe is not only a physical reality, but a profound intellectual adventure. The God equation embodies the unity of existence, the elegance of mathematics, and the promise that even the deepest mysteries of the cosmos can, in principle, be comprehended. And in that promise lies the enduring allure of physics, the beauty of reason, and the endless human quest to know the universe and ourselves fully.
So, everyone, that brings us to the end. I hope you've gained a deeper understanding from what I explained today. Let me know in the comments what kind of topics you'd like me to explore next, and subscribe to the channel so we can continue this journey of knowledge together. Because when we understand more, the world moves forward.